answers to the review problems. I think this will be a good practice for the test. Make sure you can do problems just like these. Suppose you want to find the surface area of a surface given as z equals a function of x and y. Here's how you can do it. The surface area is just integral ds over the surface sigma, which ds is this. It's an analogy to what you did in calculus 1 for arc length. Square root 1 plus dz dx squared plus dz dy squared, integrated over the region R of projection. Well, what's the projection region? I didn't draw the picture here. But this paraboloid, if you find its intersection with the xy plane by setting z equals 0, you get 0 equals 1 minus x squared minus y squared, or x squared plus y squared equals 1. You get the unit circle in the xy plane as the intersection. So the region of projection is the unit disk, the interior of that unit circle in this integral here. So to take the surface area of a surface z given as a function of x and y, just integrate over the region of projection, square root 1 plus dz dx squared plus dz dy squared. Alright, now, to evaluate a double integral, you recall, if you have a simple polar region like this, where you're, such as the unit circle, you can let theta go between two rays, here theta equals 0 and theta equals 2 pi. R go between two curves, in this case R equals 0 and R equals 1. That sweeps out the unit circle, you recall. And the dA in polar coordinates becomes R dr d theta. So there's our iterated integral that helps us to evaluate it quickly. Well, if z is 1 minus x squared minus y squared, then dz dx is minus 2x, dz dy is minus 2y. You get this integral here. Well, 4x squared plus 4y squared is 4r squared. And so now I just have to do this iterated integral. That's pretty easy. It actually splits up into the product of 2, right? Since the integral here on the inside from 0 to 1 comes out to be a constant going between two constants. You can pull it out over here and say take integral from 0 to 2 pi d theta times this integral. Pull that constant out of there. And that's what I did. And then I also said you can make a substitution. Once you pull it out, let u equal 1 plus 4r squared, so that's square root u. 1/8 du then comes out to be r dr, right? You take du is 8r dr and then divide by 8. And so, let's see. I think this should have been a 1/8 here. I forgot to go back and fix it. So it's square root u 1/8 du is what that one integral becomes. There's an 8 here. And then the integral from 0 to 2 pi d theta. This step it's back, right? The 1/2 came out as the 1/8. Integral square u to the 1/2 is u to the 3/2 over 3/2. And now you have to evaluate this integral at 1 and 5 with a substitution, right? When r equals 0, u equals 1, u equals, sorry, when r equals 0, u equals 1. That's the bottom end point. When r equals 1, 1 plus 4 is 5 is the top end point. So you wind up with pi over 6, 5 square root 5 minus 1 for the surface area. How about this one? If you have a vector valued function, it may or may not be conservative. That is, it may or may not have a potential. Well, this one I'm telling you ahead of time, it has a potential. What is it? Well, to find the potential, you know, this has to be d phi dx and this has to be d phi dy for some function phi. Being a conservative field means the gradient of some potential. So this is d phi dx. Phi must be the integral. So put phi equals this. And also for this to be d phi dy, phi must be this integral, partial integral with respect to y of this component. Right? This is the partial derivative of phi with respect to y, so you take the partial integral with respect to y, you get phi back. You find out from integrating this one, phi has to be e to the x cosine y plus any function of y. From integrating this one, you get phi s b e to the x cosine y plus any function of x. For those be equal, these two have to be the same constant. So the most general potential is e to the x cosine y plus c. I only asked you for one potential. You can choose c to be anything. So choose it to equal to 0. And you got e to the x cosine y is a potential. Now the second part of the question is, what's the value of the line integral f dot dr for this f along a curve that goes from 0, 0 to 2, 1? It actually doesn't matter what path you take. For a conservative field along any piecewise smooth path, this integral will be the same. And so its value is going to be phi at the final point minus phi at the initial point, which is e squared cosine 1 minus 1. Alright, so that's that one. Here's a vector field and a curve, and suppose in a scalar field, suppose I say verify that f is the gradient field. Well, just take the gradient of this and see what you get. The gradient is partial with respect to x times I plus partial with respect to y times j. So that gives you, well, 2x plus nothing, right? Partial derivative treats y as a constant. Nothing plus 4. And so you get those components there. Oh, that's this f. So that shows you that f is the gradient of phi. And if you want to evaluate a line integral, now that you know it's conservative, it's the gradient cell function, you can evaluate the line integral by taking phi at the last point minus phi at the first point. Plugging those in tells you that the result is 27. How about this one? Evaluate a scalar line integral. Remember, there's a vector line integral there. There's also a scalar line integral. That's just integrate whatever function it is, ds. So if I say do the scalar line integral, I'm going to give you a function, and you just take integral ds. If I give you a vector line integral, if it's conservative, you can evaluate it with a potential. But if it's not conservative, I'll show you how to do that shortly in one of the upcoming problems. So the line integral is the integral of the function ds, where ds is, well, the integral ds can be evaluated as integral over what t runs over minus 2 to 1. The function x and y written as functions of t, and then times the ds gets replaced with square root of dx dt squared plus dy dt squared dt. So you have to memorize that for the test. On a scalar line integral, you have to replace ds with all this. Right. Now, dx dt and dy dt, this is x and this is y, so the derivatives are 1 and minus 1. And I put in that x is 2 plus t and y is 2 minus t in here. And then you just have a calculus 1 integral that comes out to be 3 square root 2 over 2 minus. Here's the vector line integral. Suppose I want to evaluate this along the quarter circle in quadrant 4 traveled clockwise. So you're starting here and going from here around the unit circle. You could let x equal cosine t and y equal minus sine t. So instead of going counterclockwise, you now go clockwise, because y goes negative first instead of positive. Go from 0 to a right angle in order to traverse a quarter circle. So then, to integrate a line integral when it's not conservative, you just have to go back to this theorem. F dot dr is f dot dr dt dt. Just replace dr with dr dt dt. Easy as that. So dr dt is just the derivative of this vector, where x is cosine. It's derivative of this. It's dx dt where x is cosine minus sine. Dy dt, derivative minus sine is minus cosine. And then f is this one, x squared and xy, where you put in what x and y are in terms of t. Take the dot product of this. You actually get 0. If you integrate 0, you get 0. That's the end of that one. How about this one? If I get the vector field, you should know what the divergence and curl are. The divergence is just del dot f. So you take ddx of the first component of f plus ddy the second component plus ddz of the third, right? So ddx of this, ddy of this, plus ddz of that, all added together, really easy. You just get 2x plus 2y plus 2y is 2x plus 4y for the divergence. The curl is del cross f, where del again is this ddx, ddy, ddz. And here's f, the components of f, I, j, k, so you can compute the cross product. And when you do that, right, I multiplies this subdeterminant. This operating on this, so dy of 2yz minus this operating on this, ddz of y squared. So this one minus this one, and then minus j, remember it's minus, ddx of this minus ddz of this. I wipe out its row and column and take the subdeterminant. And then for k, we've got this subdeterminant in the corner, ddx of y squared minus dy of x squared. And it comes out to just 2zi for that one. I won't spend a lot of time on this. You can look at it at home and send me any questions you want. This is not conservative on any open region in 3D. Why not? Because the only place where the curl is equal to 0 is along the plane z equals 0. Right? In order for this curl to be 0, it's the plane z equals 0. But that's not an open three dimension. It's a plane, and it's actually a closed subspace. So there is no region anywhere where you can say this is conservative in 3 dimensions. So that's their criterion. In 3 dimensions, on a simply connected region where f is nice, we'll say, the f is conservative if and only if the curl is 0. And then you can drop the simply connected, just open connected, and if it's actually conservative, then this would have to have been 0. Evidently it's not conservative. Alright, about this one, we look at, let D be the triangular domain bounded by the x and y axes of the line, y equals 2 minus x. So I colored it in here. Here's 2 and 2, it's that triangle. Suppose I want the density function rho of xy is a function of x, alone is x. Find the total mass. So you should memorize for the test that the mass is just the integral of the density function. So I integrate x over this triangle. The triangle is a type 1 region. It goes from x equals 0 to x equals 2, then to max. And then bottom curve y equals 0 and top curve y equals 2 minus x. So it's bottom curve to top curve for y, min x to max x for x, integrates over this plane region. And now you just have to evaluate the inside integral. That's a partial integral with respect to y. So you get xy, and then plug in y equals 2 minus x and 0, and you should get that. The mass comes out to be 4/3. Now the second part actually was to compute the center of mass. For the center of mass, you first compute the moments, mx and my. So you compute my by doing the same integral. It's exactly the same one you had up here, except you stick x in. That'll give you my if you put x in. But then it goes back, compute x bar, use my. So it's just this funny notation. It means this is actually the moment in the x direction at x equals 0 meaning at the y-axis. So double integral that you had up there with x stuck in, and when you go through and evaluate it the same old style, you get 4/3. For mx, you put y in there, take the double integral that you had up there. Otherwise, you get 2/3. Consequently, the center of mass is my over m for the x coordinate. That's 4/3 over 4/3 is 1. mx over m is 2/3 over 4/3 is 1/2. So this could balance at 1/1/2 right here. Tilt it over and put your finger there. Well, how about evaluate a this looks like got a couple typos in there. Let's see. This is just the line integral. For some reason I've got a little ring on there, that indicating it's a closed path. So I'll put this for a closed path on the test. This shouldn't be the ring there, just a line integral without the circle on it. If t goes from 1 to 2 and you move along this curve, t squared 2t, you're actually tracing out a parabola. If you solve for y as a function of x, you'll get a parabola out of that. And suppose I want to evaluate this line integral, y dx minus x dy. Well, I just have to put in, here's our theorem for line, this is the same vector line integral as before, just in a different notation. You just place dx with dx dt dt, dy with dy dt dt was our theorem, and then you can evaluate the line integral between the two t values, in this case 1 and 2. So now x is t squared and y is 2t, so you put 2t for y, t squared for x, and so on. And then you just evaluate this calculus 1 integral. You get 14/3 for the line integral. Find the area of the parametric surface. This one's a little harder. We didn't have good homework on this. Just memorize this formula. I showed you in class how you can get this surface area formula, but you just take dr du cross dr dv, length of that vector, and integrate it over the region of projection. So on this one, the projection region I'm saying is u between 1 and 2 and v between 0 and pi over 2. So when I integrate over this region, and here's the cross product written as a determinant. When I integrate over that region, u goes from 1 to 2, v goes from 0 to pi over 2. It's that rectangle. And then the determinant evaluates like this. I take this times this minus this times this, right? Wiping out the row and column of I gives me minus 2u squared cosine v. Multiplying I. Now what multiplies minus v, minus j? You wipe out this row and column and you get cosine v times 0 minus a minus u sine v times 2u. Gives you this minus 2u squared sine v. And then wipe out the row and column of k. This times this is u cosine squared minus this times this gives a plus u sine squared. The whole thing just comes out to be u cosine squared plus u sine squared is u. Now the length of this is the root sum square of these things. This one squared plus this one squared plus this one squared. And when you work that out, it's 4u squared plus 4u to the 4th plus u squared integrated. That's kind of a tricky integral until you realize there's an easy substitution. If you just take a square root u squared, or take a u squared, factor it out, and the square root u squared factored out is a u outside. So u outside times this square root is algebraically equal to that on this region. And now, I can make a substitution. W equals 4u squared plus 1, and then this is 1/8 dw, and I can evaluate the integral. The integral now has to change limits because if when u equals 1, w being 4u squared plus 1 is, let's see, 4 times 1 plus 1 is 5. That's the bottom endpoint. When u is 2, 4 times 2 squared is 16 plus 1 is 17. That's the top endpoint. So that's the substitution. Then it's simple integrals after that. You get pi over 24 quantity. 17 to the 3 halves minus 5 to the 3 halves evaluates that surface area given in parametric form. This is parametric form for a surface. Just like for a parametric curve, you write x as a function of t and y as a function of t and z as a function of t. For a parametric surface, you write x, y, and z as a function of two variables, u and v, and if you do it right, you get a surface. That's commonly what you get. Okay, let's finally find the centroid of the top half of the unit disk at 0, 0. So it's a half disk, right, above the x-axis. Well, I should draw it here. I think you can see this part of the board. You look at it and you say the centroid is the balancing point when the density is 1, right? The formula for the centroid is the same as for the center of mass when you replace density delta with 1. Or you replace with any constant, cancel top and bottom. But when you replace density with 1, you get the same, you get this formula for the centroid. So this is actually the center of mass for a uniform density, 1. That means it's going to balance here, so you immediately gather that x bar equals 0, no calculation needed. Now to calculate y bar, you have to do the double integral over that half disk of y and divide by the area of the disk. So what is that? To integrate over that half disk, I let theta go from 0 to pi, and r go from the inside curve 0 to the outside curve r equals 1, right? R equals 0, r equals 1. And that sweeps out the half disk. And when you evaluate this integral, it splits up into two halves, right? Since you can pull the sine theta out because it's a constant inside the partial integration here. And then you're left with the integral of r squared dr from 0 to 1. Well, that's a constant. Since it's evaluating a constant endpoints, you can pull it out. And when you compute those, you get 4 over 3 pi. Well, I hope that helps prepare for the test. Send me questions by email if this doesn't do it for you. I checked that one typo in there. Maybe I'll get a chance to fix it before this goes up. Thank you.